Hello and welcome to Analog Edge. In this tutorial, we're diving into the fascinating world of post-layout simulation for high-speed ADCs. If you're looking to optimize your simulation time, debug errors effectively, and ensure your ADC design performs flawlessly, then this video is for you. So, let's get started. Step 1. Optimize simulation time. Post-layout simulations can take a lot of time, but by optimizing your settings, you can save hours without sacrificing precision. First, enable Spectre APS in the High Performance Simulation tab of your test editor or ADL. Spectre APS is designed to make simulations faster and more efficient by leveraging parallel processing. It's your go-to tool for saving simulation time. Next, increase the simulation frequency to FS/2. By focusing on fewer points and reducing the number of cycles simulated, you can achieve results more quickly without losing key insights. It's also crucial to let all internal signals, such as reference voltages, stabilize before you begin sampling. Skipping this step can lead to misleading results that don't reflect the actual behavior of your design. Finally, adjust the Reltal parameter in your simulator. This setting allows for dynamic adjustments to simulation tolerances, fast-forwarding the simulation process without compromising accuracy. By following these steps, you'll significantly reduce simulation time while maintaining high-quality results. Step 2. Analyze simulation results. Once your simulation is optimized, the next step is to carefully analyze the results to identify any performance issues. If the results look inaccurate at high frequencies, a good practice is to simulate at lower frequencies. This can help uncover hidden issues that may not appear at higher operating speeds. Include parasitic capacitances from the CC or RCC netlist in your schematic simulation. Parasitics can have a significant impact on ADC performance, and modeling them accurately is essential to replicating real-world conditions. If you suspect a particular block in your design is causing issues, isolate it using LVS BOX extraction. For example, if you think the comparator in your ADC is contributing to errors, you can simulate it independently with its schematic and remaining post-layout netlist views. This targeted approach helps you focus your debugging efforts where they're needed most. By analyzing your results systematically, you'll gain deeper insights into your ADC's behavior and identify potential problem areas more effectively. Step 3. Debugging with PEX Netlists. When parasitic effects distort your simulation results, debugging the PEX netlist becomes critical. Here's how you can do it. First, if unwanted parasitic capacitances are causing distortions, comment them out in the CC netlist using this command. This command will comment the CC cap between OUTP and AGND-net. Next, to address routing resistances, set them to 0 for the relevant paths. For example, to remove resistance from the OUTN1 route, use the following script. These steps allow you to help to debug, isolate parasitic effects, and get more accurate simulation results. Final checks. Before wrapping up, it's crucial to perform a few final checks to ensure your design is ready for real-world operation. First, validate all signal paths to make sure supplies, grounds, and connections are fine. A small mismatch in these paths can lead to significant performance issues. Next, simulate your design under extreme conditions. This might include variations in power supply, temperature, or signal transitions. Testing your ADC in these scenarios ensures it's robust and can handle unexpected challenges. Finally, ensure your ADC startup sequence is stable. Check that all signals and components initialize properly during power-up and that the ADC achieves a steady-state operation before sampling begins. And that's it. By following these steps, you'll have a comprehensive understanding of how to optimize, analyze, and debug your high-speed ADC design.